In the winter of 1943, Japanese naval intelligence officers gathered in a windowless briefing room beneath the Imperial Navy Ministry in Tokyo, reviewing reconnaissance reports that should have been impossible. American bombers had struck the logistics depot at Rabaul with surgical precision at 0200 hours, in weather conditions that reduced visibility to less than 50 meters, hitting fuel storage tanks that measured 30 meters across from an altitude of 7,000 feet. The strike was not an outlier. It was the fourth such nocturnal precision raid in as many weeks. The officers faced a ballistic anomaly that their doctrine had no framework to explain. The Americans had somehow bypassed the fundamental limitations of human vision and turned the night sky into an operational asset. What followed was not merely a tactical adaptation, but a complete strategic collapse, as Japanese commanders realized they were fighting an enemy that had industrialized darkness itself. The myth that Japanese planners had constructed was mathematically sound, rooted in observable evidence from the European theater and the known limitations of contemporary aviation technology. Night bombing, as practiced by the Royal Air Force over Germany, was a blunt instrument. British crews scattered ordnance across entire urban grids, relying on incendiary saturation rather than precision. Post-raid reconnaissance photos showed impact patterns that resembled shotgun blasts, with only a fraction of bombs landing within a kilometer of their intended targets. Japanese strategic analysts had studied these operations exhaustively and concluded that the vast distances of the Pacific theater would amplify every inefficiency. A formation of B-17 flying fortresses required visual contact between aircraft to maintain cohesion. Remove daylight, and formations would scatter across hundreds of square miles of ocean. Navigation over water in darkness relied on dead reckoning and celestial observation, methods that accumulated error at a rate of roughly 5 miles per hour of flight. A 6-hour night mission from Guadalcanal to Rabaul meant crews could miss their target by 30 miles or more, searching blindly for an island that represented less than 1% of the visible horizon. The fuel mathematics seemed equally prohibitive. A fully loaded B-24 Liberator consumed 210 gallons per hour at standard cruising power. Night operations required crews to maintain higher power settings for extended periods, both for safety margins and to compensate for navigational uncertainty. This pushed consumption closer to 240 gallons per hour, reducing operational range from the advertised 2,100 miles to barely 1,600 miles under combat conditions. Japanese planners calculated that American bombers launching from bases in the New Hebrides would reach Rabaul with perhaps 90 minutes of fuel reserves, leaving no margin for weather diversions, combat maneuvering, or navigational error. The entire operational concept appeared to violate basic principles of aerial warfare logistics. Tokyo's strategic audit concluded that nocturnal raids would remain what they had always been, occasional harassment missions flown by expendable crews in obsolete aircraft, more psychological theater than genuine military threat.
They had audited the aircraft but failed to audit the system. The Americans were not attempting to extend existing daylight tactics into the darkness. They were engineering an entirely new form of warfare built on 3 technological foundations that Japanese intelligence had observed in isolation but never synthesized into a coherent threat assessment. The first element was airborne radar, specifically the SCR-720 unit that American engineers had miniaturized to fit in the nose cone of a PV-1 Ventura or the tail turret of a B-24. This was not the crude early warning radar that both sides had deployed along coastal installations. This was target acquisition radar, capable of painting a detailed picture of surface features from 25,000 feet in absolute darkness, distinguishing between a cargo vessel and a destroyer at ranges exceeding 12 miles. The second element was the low-altitude bombing radar, known simply as LABS, which translated those radar returns into release calculations, feeding data directly to the bombardier in real time. The third element, the one that transformed individual capability into strategic dominance, was the training infrastructure. The Americans had built an entire nocturnal aviation industry with dedicated night combat schools at Hammerfield in California and Boca Raton in Florida, where crews flew 300 hours in blackout conditions before ever seeing a combat assignment. The kinetic reality announced itself over Rabaul on the night of November 2, 1943. Japanese air defense commanders had positioned their forces according to established doctrine. Fighter squadrons stood down at sunset, their pilots resting for the inevitable dawn patrols. Anti-aircraft batteries maintained skeleton crews, enough to respond to harassment raids, but not enough to sustain intensive operations. Coastal observation posts tracked the sunset and sent the all-clear signal to fleet anchorage at Simpson Harbor, where 19 naval vessels and 43 cargo ships had gathered to await the cover of darkness for unloading operations. At 2300 hours, radar operators detected a formation inbound from the southeast, altitude 8,000 feet, airspeed 190 knots. The profile suggested a reconnaissance sweep, a single flight of perhaps 3 aircraft. Standard protocol called for searchlight illumination and scattered anti-aircraft fire, enough to disrupt the intruders without wasting ammunition on targets that posed no immediate threat. The first bombs impacted the fuel depot on the eastern shore of the harbor at 23:13 hours. Not near the depot, on it. 4 direct hits on storage tanks that measured 32 meters in diameter, creating a fireball visible from 40 miles out to sea. In the orange glow of burning aviation fuel, Japanese gunners saw what their radar had failed to communicate. Not 3 aircraft, but 17, arranged in a precise bombing formation, each plane maintaining exact station intervals of 200 meters, releasing ordnance in a sequenced pattern that walked explosions across the entire logistics complex. The second wave arrived 4 minutes later, using the light from the first fires to refine their own targeting solutions. By 23:30 hours, the entire eastern shore of Simpson Harbor was engulfed in flames, and American bombers were already turning south, disappearing into the darkness before Japanese night fighters could even scramble from their dispersal areas. The psychological impact rippled through Japanese command faster than the actual damage reports. If the Americans could execute coordinated precision strikes in total darkness, then the fundamental rhythm of Pacific naval operations had just collapsed. Japanese doctrine relied on a predictable cycle: disperse and hide during daylight hours when American reconnaissance could find you, then concentrate and operate under the protection of night. That protection had just been revoked. Every anchorage, every supply depot, every troop concentration now existed in a state of permanent vulnerability. There was no safe hour, no operational pause, no moment when forces could stand down from full combat readiness. The industrial capacity that sustained these raids is where the strategic audit becomes genuinely terrifying from the Japanese perspective. Each precision night raid required not just trained crews and specialized aircraft, but an entire logistical lung that stretched back across 7,000 miles of ocean to manufacturing centers in Southern California and training facilities in the American Southwest. The Americans were not diverting resources from daylight operations to make night raids possible. They had constructed parallel production lines specifically optimized for nocturnal warfare. At the Consolidated Aircraft Plant in San Diego, one assembly line produced standard B-24 Liberators for daylight bombing squadrons. A separate line, running simultaneously, produced radar-equipped variants fitted with AN/APQ-13 bombing radar, flame-dampening exhaust systems, and night-optimized instrument panels with red lighting that preserved crew night vision. These were not field modifications. They were purpose-built combat systems rolling off the factory floor at a rate of 6 aircraft per day. The training infrastructure represented an even more profound investment. The Navy's Night Combat Training Program at Barbers Point in Hawaii processed 240 pilots every 8 weeks, putting them through a curriculum that included instrument-only navigation, radar interpretation, low-altitude strike tactics, and crew coordination in complete darkness. The program had a 30% washout rate, not because of pilot error, but because the Navy maintained uncompromising standards for nocturnal competency. For every crew that deployed to combat squadrons in the Solomons or the Marianas, 3 crews had been trained, ensuring a constant flow of replacement personnel with hundreds of hours of night flying experience. Japanese training programs, by contrast, were struggling to maintain daylight proficiency, cutting advanced training hours to rush pilots into combat units that were hemorrhaging experienced flyers at unsustainable rates.
The fuel equation that Japanese planners had deemed prohibitive had been solved not through engineering miracles, but through systematic industrial brute force. American logistics officers had calculated that sustaining night operations across the Pacific required approximately 40 million gallons of aviation fuel per month positioned at forward bases. Rather than treating this as an impossible demand, they had simply built the infrastructure to deliver it. Fleet oilers running regular routes from Pearl Harbor to Espiritu Santo moved fuel in bulk quantities that would have supplied the entire Japanese naval air arm for half a year. Submarine tenders at forward anchorages carried fuel purification equipment that could process seawater-contaminated avgas back to combat-grade specification, recovering thousands of gallons that would otherwise have been dumped as waste. At Munda Airfield in the Solomons, CB construction battalions built underground fuel storage capable of holding 3 million gallons, protected by 12 feet of coral and concrete against Japanese counterstrikes that never materialized because Japanese bombers lacked the nocturnal navigation capability to find the facility in darkness. The Americans had turned logistics itself into a weapon system, and the industrial mathematics behind it revealed the true scale of the mismatch. In 1943, the United States produced approximately 96,000 aircraft. Japan produced 16,000. But raw production numbers obscured the more devastating reality. American aircraft rolled off assembly lines already equipped for night operations, while Japanese fighters and bombers required extensive field modifications to attempt even basic nocturnal intercepts. An F-6F Hellcat delivered to a carrier squadron arrived with functioning radar, night-optimized gun sights, and standardized instrument panels that allowed pilots to transition between aircraft without relearning cockpit layouts. A Japanese A-6M0 arriving at a forward airfield carried none of these systems and would not receive them because the industrial capacity to produce such equipment at scale simply did not exist within the Japanese manufacturing base. The cascading effects of American night superiority manifested in ways that went far beyond simple bomb damage. Japanese convoy schedules, which had relied on darkness for protection, had to be completely restructured. Cargo vessels that previously made the run from Truk to Rabaul in a single overnight passage now required 3 nights, hugging coastlines and sheltering in small harbors during the hours when American patrol bombers operated with greatest efficiency. This tripled transit times and meant that the effective carrying capacity of the entire Japanese merchant fleet dropped by 60% without a single ship being sunk. The logistical lung that supplied forward bases began to constrict not from lack of vessels, but from the simple mechanical fact that ships were spending more time hiding than moving. Japanese air defense doctrine, which had been built around visual acquisition and daylight intercepts, proved nearly worthless against nocturnal attackers. A Zero pilot scrambled to intercept a night raid faced a mathematically impossible problem. American bombers operated at altitudes between 7,000 and 9,000 feet. Visual acquisition range on a moonless night was approximately 400 meters. To intercept, the Zero had to be within 400 meters of a bomber's flight path at the correct altitude at the exact moment the bomber passed that point in 3-dimensional space.
The Americans were operating in a combat volume that measured roughly 300 cubic miles. The odds of a random intercept were effectively zero. Japanese night fighter pilots began to report a phenomenon they called ghost formations, where radar would detect American aircraft but visual contact would never materialize, leaving pilots to burn fuel in futile searches until they had no choice but to return to base. The Americans, meanwhile, had inverted the entire problem. Their bombers carried AN/APS-15 tail warning radar that could detect pursuing fighter at ranges exceeding 1,200 meters, 3 times the distance at which the Japanese pilot might achieve visual contact. American tail gunners received electronic alerts of approaching aircraft and could begin defensive fire using radar-directed streams of tracer rounds that served as visual references for correcting aim. Japanese pilots found themselves in the nightmare scenario of being detected, targeted, and fired upon by an enemy they could not see. After-action reports from surviving Zero pilots described watching tracer fire arc toward them from complete darkness, with no visible aircraft, no exhaust flame, nothing but the sudden geometric certainty of bullets converging on their position. By the spring of 1944, Japanese defensive planning had shifted from attempting to stop night raids to simply surviving them. Logistics depots were dispersed into smaller caches hidden under jungle canopy. Fuel storage was distributed among dozens of small tanks rather than concentrated in large facilities. Ships in harbor maintained steam in their boilers around the clock, ready for emergency dispersal at any moment. These were not tactical adaptations, they were the defensive postures of an enemy that had lost control of an entire dimension of warfare. Every measure taken to reduce vulnerability to night attack also reduced operational efficiency. Dispersed fuel storage meant trucks spent more time driving between caches. Ships maintaining constant steam readiness burned fuel even while anchored. The cumulative effect was a slow industrial asphyxiation, where Japanese forces were consuming their logistical capacity just to maintain defensive readiness, leaving less and less available for offensive operations. The delayed realization, the moment when Japanese strategic planners fully understood the scope of their predicament, came not from a single catastrophic raid, but from the accumulation of operational data over 6 months. Intelligence officers compiled loss reports and discovered a pattern that contradicted every assumption about aerial warfare economics. American night raids were achieving higher accuracy rates than Japanese daylight raids with lower loss ratios. A typical American night strike against Truk in early 1944 involved 12 aircraft, delivered an average of 78 tons of ordnance, achieved a circular error probable of 45 meters, and lost 0 aircraft to enemy action. A comparable Japanese daylight raid against American positions at Guadalcanal required 30 aircraft to deliver 60 tons of ordnance, achieved a circular error probable of 200 meters, and lost an average of 4 aircraft per mission. The Americans were not just winning the night battle, they were conducting nocturnal operations more efficiently than Japan could conduct daylight operations. The industrial explanation was straightforward but devastating. American crews were operating within a system that had mechanized every element of mission planning, navigation, targeting, and battle damage assessment. Before a single aircraft launched, weather officers provided updated wind calculations based on reconnaissance flights and meteorological modeling. Navigation officers plotted courses using Loran radio navigation, a system that provided position fixes accurate to within 2 miles across thousands of miles of ocean. Bombardiers received pre-calculated release points based on radar returns, wind data, and aircraft performance characteristics. After the raid, photo reconnaissance aircraft equipped with flash bombs and night cameras documented the results, feeding data back into the planning cycle for the next mission. The entire process functioned like a production line, with quality control checkpoints and continuous refinement. Japanese mission planning, by contrast, remained a largely manual process dependent on individual pilot skill and experience. Navigation relied on dead reckoning and visual landmarks. Targeting depended on visual acquisition.
Battle damage assessment consisted of pilot reports, which were notoriously unreliable and impossible to verify. There was no systematic feedback loop, no industrial process for converting operational data into improved performance. Each mission was a discrete tactical event, and lessons learned in one operation had no reliable mechanism for propagating to the next. The Americans had built a learning system. The Japanese were fighting with artisan-level craftsmanship against mass-production methodology. The psychological toll on Japanese aircrew morale became its own strategic factor by mid-1944. Pilots who had trained for daylight combat suddenly faced an enemy that struck from darkness with mechanical precision. The warrior ethos that sustained Japanese military culture emphasized courage, skill, and willingness to sacrifice. But those virtues offered no advantage against an enemy you could not see, could not catch, and could not predict. Night fighter pilots began reporting stress reactions that Japanese military medicine had no framework to address. Auditory hallucinations of engine noise, compulsive scanning behavior that persisted even on the ground, and a profound sense of helplessness that corroded the fundamental identity of being a combat pilot. These were not cowards, they were skilled aviators whose training and doctrine had become obsolete, forced to operate in conditions where courage and skill were irrelevant variables. American crews, meanwhile, operated in a psychological environment that reinforced competence and control. They flew aircraft equipped with multiple redundant systems. If primary radar failed, backup systems existed. If navigation instruments malfunctioned, Loran provided an independent position fix. If weather closed in around the target, alternate targets had been pre-briefed with complete navigation data. The mission architecture assumed things would go wrong and had engineered solutions in advance. This created a psychological buffer where crews could maintain operational focus even under stress because the system itself was designed to absorb individual failures without mission collapse.
The strategic impact of sustained American night operations extended beyond immediate bomb damage into the realm of operational paralysis. Japanese commanders faced a resource allocation problem with no satisfactory solution. Maintaining round-the-clock air defense required double the personnel, double the fuel consumption, and double the maintenance overhead. Fighter squadrons that previously operated on a single daylight shift now needed pilots and ground crews for nocturnal rotations. This meant that the same industrial capacity that was already struggling to replace combat losses now had to support twice the operational tempo with no increase in production output. Anti-aircraft batteries that could stand down 12 hours per day now required continuous manning, which meant gun crews worked shorter shifts, accumulated fatigue faster, and showed degraded performance across both day and night operations. The Americans had found a way to multiply the effective consumption rate of Japanese military resources without firing a shot. The mathematical elegance of this strategic stranglehold becomes clear when examining fuel consumption data from Japanese naval air operations in late 1944. A fighter squadron based at Rabaul that previously consumed 18,000 gallons of aviation fuel per week in 1942 was burning 42,000 gallons per week by October 1944, despite flying fewer combat missions. The difference was entirely attributable to defensive readiness postures necessitated by the threat of night attack. Aircraft sat on runways with engines warm, ready for immediate scramble. Patrol flights ran continuous coverage rather than timed sweeps. Pilots conducted instrument checks and system tests in darkness, burning fuel to maintain proficiency in conditions they had never been trained for. The logistical lung was gasping, consuming its own capacity to sustain itself, while the actual combat effectiveness of those defensive measures approached zero. American intelligence officers monitoring Japanese radio traffic began to detect a shift in operational language that signaled a deeper psychological fracture. Japanese air controllers stopped issuing intercept factors for night contacts. They simply broadcast warnings that American aircraft were in the area and left individual pilots to respond as they saw fit. This was not tactical flexibility, it was command abdication, the acknowledgement that central coordination had become pointless when the enemy operated beyond the effective range of your defensive systems. Fighter pilots reported contacts that they could not pursue. Radar operators tracked formations they could not intercept. Anti-aircraft batteries fired at altitudes and bearings that produced no observable results. The entire defensive apparatus had become a theatrical performance, actions taken because doctrine demanded them, not because anyone believed they would alter the outcome. The industrial response that Japan attempted in early 1944 revealed the fundamental asymmetry in manufacturing capacity. Japanese aviation engineers began a crash program to develop night-capable variants of frontline fighters, fitting the J-1 and Gecko with primitive airborne radar and training specialized night fighter units. The program achieved some tactical successes. Night fighter ace Sakai Saburo documented several confirmed kills of American bombers in nocturnal engagements, but the scale of the response illustrated the depth of the problem. By June 1944, Japan had produced approximately 50 radar-equipped night fighters. In the same period, the United States had produced over 800 radar-equipped patrol bombers, 700 night-capable carrier fighters, and retrofitted another 1,200 heavy bombers with advanced navigation and targeting systems. The ratio was 16 American night-capable aircraft for every Japanese night fighter, and that ratio was widening every month.
The Gecko night fighters themselves demonstrated the material constraints that limited Japanese responses. Each aircraft required approximately 400 hours of skilled labor to install and calibrate radar equipment, work that had to be done by hand because Japan lacked the industrial infrastructure for standardized electronics production. American radar sets were manufactured on assembly lines by workers with minimal technical training because the units were designed for field replacement rather than expert installation. A damaged ANAPS-6 radar could be swapped out in 40 minutes by a crew chief with basic electrical knowledge. A damaged FD-2 radar in a Gecko required the aircraft to be pulled from service and sent to a depot facility where specialists would spend 3 days diagnosing and repairing the system. The Americans had engineered for mass production and field maintainability. The Japanese were still crafting precision instruments that only specialists could service. The cumulative effect of these industrial and tactical asymmetries manifested in shipping losses that accelerated throughout 1944. Japanese merchant vessels attempting to supply forward bases faced a gauntlet where the traditional protection of darkness had been stripped away. American PBY Catalinas and B-24 Liberators equipped with ASV radar patrolled designated sea lanes throughout the night, detecting ships at ranges exceeding 20 miles. Once detected, a target had virtually no chance of escape. The attacking aircraft could track the vessel continuously on radar while positioning for attack runs, dropping flares for visual confirmation, then executing bombing or torpedo attacks from altitudes and angles that Japanese deck gunners could not effectively engage. In the first 6 months of 1944, Japan lost approximately 400,000 tons of merchant shipping to nocturnal air attack, losses that were strategically equivalent to a medium-sized naval battle occurring every single week with no Japanese response capability. The Americans had identified and exploited what systems analysts would later call a critical path dependency. Japanese military operations required a functioning logistics network to move fuel, ammunition, and reinforcements from rear areas to combat zones. That network depended on merchant shipping. Merchant shipping had traditionally depended on darkness for protection from air attack. By eliminating the protective value of darkness, American night operations had severed the critical path, and every downstream system began to fail in sequence. Bases ran short of fuel because tankers could not make the transit. Infantry units ran short of ammunition because freighters sheltered in harbors rather than risk nocturnal passages. Air squadrons could not relocate because the transport vessels that would move ground crews and equipment were bottlenecked in rear areas, waiting for a safe transit window that no longer existed. Japanese strategic planning documents from mid-1944 reveal commanders grappling with a problem they described as temporal compression. The protective cycle of day and night that had structured all previous military operations had collapsed into a single continuous operational period where the enemy could strike with equal effectiveness at any hour. This was not simply a tactical inconvenience. It represented a fundamental revision of how military forces could be organized and employed. Commanders could no longer plan operations using darkness as a guaranteed safe period for logistics, repositioning, or rest. Every plan had to account for continuous vulnerability, which meant every plan required more resources, more time, and more redundancy than the resource base could support. The strategic audit revealed an impossible equation. Defending against American night operations required resources that could only be delivered by a logistics network that could not function while under threat from those same night operations.
The legacy of American night raid doctrine extended far beyond the immediate tactical victories in the Pacific Theater. What American aviation engineers and operational planners had accomplished was the creation of an all-weather, around-the-clock bombing capability that transformed air power from a daylight-limited tactical tool into a strategic instrument that could apply pressure continuously without respite. The industrial systems that made this possible, the radar manufacturing capacity, the specialized training infrastructure, the logistics networks capable of sustaining complex operations across oceanic distances, these became the foundation for American air power doctrine in every subsequent conflict. The crews who flew those night missions over Rabaul and Truk returned home and trained the next generation of pilots who would conduct night operations over Korea, over Vietnam, over Iraq. The institutional knowledge, the technical specifications, the operational procedures, all of it was preserved and refined and passed forward. The B-29 superfortress raids that eventually burned Japanese cities starting in 1945 were the direct descendants of those early night precision raids over the Pacific. The aircraft were larger, the radar more sophisticated, the bombing altitudes higher, but the fundamental concept remained unchanged. Use technological superiority to operate in conditions where the enemy cannot effectively respond. Apply that capability systematically rather than sporadically, and sustain operations at a tempo that the enemy's industrial base cannot match. The firebombing of Tokyo in March 1945, which killed more than 100,000 people in a single night, was not an aberration or a moral collapse. It was the logical endpoint of a doctrine that had been refined over 2 years of nocturnal operations, a demonstration of what happens when one side achieves absolute dominance in a dimension of warfare that the other side cannot contest. For the generation of American veterans who flew those missions, the memory carried a particular character that separated it from daylight operations. There was a loneliness to night combat that even the most intense daylight battles did not replicate. You could not see your wingman except as a faint shadow against the stars. You could not see the target until the moment bombs fell and fires ignited. You could not see the enemy fighters that radar warned were approaching from below. Everything depended on instruments, on faith in systems, on trust that the industrial apparatus that put you in that aircraft had engineered solutions for problems you might not even recognize until they killed you. The crews who mastered that environment, who learned to trust their instruments more than their instincts, who flew hundreds of hours in darkness and returned, they carried a quiet professional pride that came from operating at the edge of human capability, multiplied by American industrial precision.